So we talked about the coin and textbook thing yesterday and the day before, and I asked you to think about how you would find the coefficient of friction of the coin on the book using only a ruler. And some of you got it. Who wants to volunteer their answer? DJ.
Our answer that we got was 0.64.
0.64?
Yeah.
Okay, so what did you get for the length of the textbook?
We got 9.625.
9.625 centimeters?
Inches.
You used inches?
Yeah.
Okay, it'll still work with inches. Okay, so 9.6 inches. And what did you get for the height when the textbook was open?
3.75.
3.75 inches. Inches. Okay, let's try to use standard units in the future. But let's talk about this. We're basically creating an inclined plane from our book. We're opening the book and creating an inclined plane where we have a vertical distance y and a horizontal distance x. What two vectors are equal when it starts moving?
Force parallel and force friction.
Yeah. The force friction. In what direction does the force friction act?
Up the plane.
Up the plane. So we got our coin. Here the coin is going to be represented by a big box. So there's a force of friction up the plane, and what else?
Force parallel down the plane.
Force parallel down the plane. And at the moment the coin starts moving, those two vectors are equal. Nod your head if you agree with me so far. Sounds good. Okay. So we learned from our notes that force parallel is a component of gravity. How do I get it from gravity? Yeah. Sine theta. And the theta is that inside angle there. Force friction is equal to what?
Force gravity. Cosine theta.
And what's the important thing right here? So you just gave me force normal. You said force normal is Fg cosine theta?
Yeah.
So what goes before force normal?
Mu.
Mu. So force of friction is mu Fn. Okay. Give me a thumbs up if you're with me so far. All right, cool. So it looks like most of us. Any questions about what I've written so far? John.
Okay, so we know that force parallel is Fg sine theta.
Yes.
But for the experiment, we're not allowed to weigh it, so we can't find Fg per se.
Correct.
So how will we determine force parallel?
Excellent question. We're not going to. What we are going to do is take advantage of the fact there's an equal sign and try to get as many variables to cancel as we can. So we're going to put the two things we said are equal. We're going to say that force parallel is equal to force of friction. And force parallel is Fg sine theta. Force of friction is mu Fn, which is Fg cosine theta. From what I've written up there, do you see how we're going to be canceling out variables? What immediately jumps out and says, cancel this? Michael?
FGs.
Yeah, the FGs. So we're going to cancel out the FGs because they're on both sides. Mass times gravity, gone. And the mu, it pops right out at us. What we find is sine of theta equals mu cosine theta. And if I want to get mu all by itself, mu becomes what? Tangent theta.
But Mr. Byers, we can't find the angle. You said no protractors.
What is tangent theta?
What I did is,
Y over X.
Go ahead.
well, what I did was I went home and put a coin on a book I had laying around.
Uh-huh.
And I took the ruler and I measured about how high it took until the coin started sliding.
Mhm.
I found that, and then I measured the length of the book and made a triangle out of that.
Which is exactly what you're supposed to do. Well done. So yeah, so we don't have, we're not going to use a protractor. What we are going to do is realize that tangent is opposite over adjacent. So if this is our angle, that's our opposite, and that's our adjacent. So mu equals the opposite, 3.75 inches over 9.6 inches. So what did you find for the mu? What was the friction coefficient?
Point 391.
0.391? Excellent. Well done. Is that what you got?
Well, I used centimeters, so I got 0.33.
Okay. But about 3 to 4?
Yeah.
Excellent. That's exactly what you're supposed to do. You need to be ready for these exercises that don't have numbers or that severely limit what you can calculate or what you can measure. Not only in physics AP, but in more advanced courses, in some math classes, you'll get exercises where you're not given any numbers, you're only given formulas. So if I said, without any formulas at all, what would it be? You would say, oh, it's just the x over the y, or the y over the x. Make sense? Okay, cool. Are there any questions about that before we move on to the next thing? Okay. At the end of the day, what I'd like you to do is staple your papers together, turn them in when they're complete, make sure they're complete. What I'd like you to do now is talk about the last thing we need to talk about for forces, and that is tension. Tension is kind of like a normal force in a cable or a rope. Tension is kind of like a normal force in a cable or a rope. I have up here a pulley and then a light string over the pulley connected to 2 spring scales that are identical. And then from each of the spring scales, I'm going to hang a 500-gram mass. And the spring scale gives me the tension in the string here and the string here. So this is a pulley, spring scale and string. The force meters, or force scales, give me 5.5 newtons. So 5.5 newtons, this is about half a kilogram. This is about another 50 grams there. Take a look at these two things. One represents an elevator. One represents the counterweight to that elevator. Which, by the way, I did some research. Counterweights are usually about 40 to 60% of the maximum weight of the occupants plus the elevator. They take the elevator's weight, and then they add 40 to 60% of the maximum occupancy and add that to the weight of the elevator. Why do they use counterweights in elevators? Seems like a lot of wasted metal. There's a motor to make you up and down. That's exactly right. Yeah, that's exactly right. It doesn't want to overdo the motor. It's really easy. If you have 2 weights that are equal on both sides, it's very easy to move them. It doesn't take a lot of oomph to move them if all you have to do is give one a little shove. So the motor ends up being pretty small in comparison. By the way, I was talking about this as people came in. I did some more research. Despite what you see in Hollywood, elevator accidents are extremely rare. An elevator hasn't fallen on someone in 100 years in the US. Because there are tons of things to get in the way. There's electromagnetic and mechanical brakes. There are multiple redundant cables over the pulley. And there's a giant spring in the pit. So, yeah, over 100 years has gone by and no one's actually been crushed by an elevator. Despite what you see in the terrorists in Hollywood, they're like, we set a bomb. You know, it never happens. But back on topic. Yeah, back on topic. So it doesn't take a lot of oomph to get the elevator moving. There's something kind of interesting, though. If I was to hold this 2 kilogram mass in my arm and lift it up very quickly, what do I feel? The weight plus more. You've all been in an elevator. When the elevator starts going up, what do you feel? Ooh, feel a little heavy. And when the elevator goes down, what do you feel? Ooh, feels a little light. Okay, so yeah, and that has to do with what you feel, the tension that your legs are pushing up on your body, and the tension that your feet are feeling from the floor. So tension is like the normal force in the cable or a rope. And it has some formulas. If the elevator is moving up, the tension is mg from the weight of the elevator plus ma from the motion. So the elevator is moving up. The tension in the cables above the elevator is mg from the weight of the elevator plus ma for the acceleration, if you will, of the elevator. If that's what the tension is as the elevator goes up, what do you think the formula is for the tension of the elevator as it goes down? Subtract, exactly. It's going to be mg minus ma. This is when it goes down, you feel, ooh, just a little second, feel a little bit lighter. All right, so our model here, 5.5 newtons. If you're really close, if you're in the front row, you might be able to see what happens as we move up and down. You see what's happening to the force, the spring scales? Yeah, it's going up as high as 600 when I allow it to go up, and as down to 400 when I go down. So it's changing a lot. Like 650 down to 700, that went all the way down to 350. So when this one goes up, the spring scale goes down. Oh, the spring scale is upside down, by the way. 10's here, 1's here. So when I go up, look what happens to the spring. Less force. When I go down, notice what happens to the spring. It's more force. Okay? Does that make sense? I have a model of the situation right here. Here we have a pulley. We have a mass 1 and a mass 2, and they're accelerating this way, and a tension 1 and tension 2. What I need from you is the mass of the objects. What is the mass of mass 1? 12? 12. Okay, 12. It's 12 kilograms. It's an elevator for mice. It's 12 kilograms. And what's the mass of mass 2? Realizing that mass 1 is going to go down. What's the mass of mass 2? 6? 8? 8. Split it in half, 7. Okay, so 7 kilograms. All right. Is there a way for us to figure out the acceleration of the two bodies as mass 1 goes down and mass 2 goes up? You better believe it. This is the formula. We all talked about F equals ma, force equals mass times acceleration. What if you have two objects involved? It's not F equals ma anymore, it's F net equals mass total times A, or rearranged, acceleration equals force net over mass total. And that's what we're going to calculate. We want to find out what is the acceleration of the two bodies, of mass 1 going down and mass 2 going up. Is this something you think you can do on your own, or should we walk through it? Let's walk through it. Okay. First thing, I need a force net, which means I need forces. what forces am I going to use? Yeah, mg, weights. So the Fg of 1 and the Fg of 2. What's the weight of 1? Yeah, 12 times 10. So 120 kilograms? Sorry, 120 newtons? I was going to say. Okay. And the weight of object 2? 70? Yeah. And then we need the force net. The net force. Now, realize, am I going too fast? Okay. Give me a thumbs up if you understand where those numbers came from. Okay, question. Because in order to turn a mass into a weight, we multiply it by the acceleration due to gravity. So 7 kilograms has a weight of 70 newtons. 12 kilograms has a weight of 120 newtons. Now, understanding, does that answer your question?
Yeah.
Okay. Now, understanding that the weights are pushing down, we would think, oh, they're both vectors are down. We should add them. But one of those vectors is acting over a pulley. So on this side of the pulley, one vector is up and one vector is up and one vector is down. And on this side of the pulley, one vector is down, one vector is up. Does that idea make sense? Because the vector, we look at either side of the pulley. Okay. So what is the net force?
Right now.
When they move. When they move.
Oh.
Yeah, right now, obviously 0. But when they move, what's going to be the net force of our two theoretical masses?
The acceleration times the total mass.
No, just the net force. We'll get there. But just the net force.
Oh. You just want to guess?
No, you don't have to guess. We have one vector pulling down at 120 and one vector pushing up at 70.
109.
So 120 minus 70 is 50.
Exactly. 50 newtons. So we have a net force of 50 newtons. Okay, let's pause there for a second. Even though both are weights, on one side of the pulley, this weight is pulling down, but this weight over here is pulling up, because it's acting over a pulley. On the other side of the pulley, this weight's pulling down, this weight's pulling up, because it's acting over a pulley.
Okay.
Oh, yeah, that's right. That's perfectly fine. Okay, does that idea make sense?
Yes.
Okay, so we move on? Yes.
So the left side is pulling down at 120, and it's also pulling up on the right side at 120?
No. The left side is pulling down at the 120,
Uh-huh.
but the right side is pulling down at 70, which means over the pulley, it's pulling up at 70. So if we were to draw the vectors, we would have the 120 pulling down on this side,
Uh-huh.
but the 70 pulling up on that side.
Right, that's what I meant. I don't know if that's what I
Oh, okay.
said, but that's what
Then yes.
I okay.
Yeah. Because they're acting over a pulley, the pulley reverses the direction of the force. So the net force is 50 newtons down on this side. So, what's the acceleration? Acceleration is our force net over mass total. Yes.
Just curious, how do you, is 70 like a real number? Is that pretty much 60% of 120?
No. You guys gave me seven kilograms. You said that's what M2 was. So that sounded good.
Alright, I see it now.
Yeah. We're doing it this way because I can show you that no matter what the numbers are, as long as mass 1 is larger than mass 2, then we'll be good. Hey, has anybody calculated the acceleration? 2.6? 2.6? 2.6?
Yes.
Sounds good? Okay, 2.6. 2.6 meter per second squared. All right, so
So wait, the net is acting on the lowest wave, right?
the net is acting on both of them.
Okay.
It's a tension that's going to act on both sides. In fact, one of the important things I didn't mention that I was going to get to, but I'll go ahead and get to now, the tension on both sides of the pulleys must be equal. The tension on both sides of the pulleys must be equal. And the net force acts on both of them. Now, I've just made the claim that the tension T1 on the left is equal to the tension T2 on the right. Can we prove this? Yes, we can. We're going to use these formulas to find the tension on either side of the pulley. T1 on the left with the 120 Newton weight, T2 on the right with a 70 Newton weight. So let's do that. So T1 is going to be the tension on one side, T2 is going to be the tension on the other side. I would like you to calculate those. Yes, please.
Oh.
I thought we were just watching you work.
I mean, it's pretty much what was possible.
Yeah. I read one time that school is where kids go to watch adults work. Yeah.
Is the G and the T formulas, is that gravity?
It is. And you can go ahead and use 10. Yeah, G is 10. You can go ahead and use 10.
I got 88. You have T2. But it's supposed to be 88.
And by the way, this will be up here during the unit. When we get to energy and simple machines, we'll add more pulleys. But you're welcome to play with this. Prove it to yourself that the weight actually does change, or the tension actually does change as it moves around. Okay, so T1, M1 times G. Hopefully that's still our weight. So this is M1G plus or minus? Minus MA. 120 minus the mass of 12 times the acceleration of 2.6. What did we get for the tension on the left side? 88.8? Wow. We're going to the future. Okay, 88.8 newtons. And T2, we have our 70 newtons plus 12 times 2.6, sorry, 7 times 2.6. What'd you get here? 88.2. Okay, sounds good. So we did use 9.8 or 10 instead of 9.8. We had to round a few times, but they should be equal, and they are. Question?
Why did you use 120 if M1 is 12?
Because the 12 of mass times the 10 for gravity.
Oh, duh.
Yeah, good question. Other questions? Yes.
So they're not exactly equal, but they are within relative.
They are absolutely equal when we round at the right times.
Okay.
Yeah. Okay. Other questions? I have one more thought experiment for you. What if, instead of being hung over a pulley, we had this scenario? What if we had a plane and a pulley, and we put M1 on a plane, hung it over a pulley, and put M2 hanging and able to fall? Would we expect the same acceleration? So this is what's happening. M1's on a frictionless plane, attached to a string, hung over a pulley at 90 degrees, M2 is allowed to fall. So when we allow it to move, M2 is going to fall, and M1 is going to move horizontally. Would we expect their acceleration to be the same?
No.
Why not? Exactly. Only one has gravity acting on it, M2. The formula is still the same. Acceleration is still F net over mass total. But now, our F net is very, very different. What is our F net? This is our 7 kilogram mass. This is our 12 kilogram mass. What is F net? Is it the 120? Well, DJ just mentioned that we only have one mass upon which gravity is acting.
So then it would just be 70.
So it would just be the 70 newtons. So the F net would just be the 70 newtons. Do we both think we hit the both of the masses?
Yeah.
Are they still connected to each other?
Yeah.
Yeah. They're still connected to each other. So this is 19 kilograms. So what's the new acceleration?
3.7.
How much?
3.7.
3.7 meters per second squared. Okay. Yes?
So they only can affect the F net if they have gravity acting upon it.
Yes. If their vectors are parallel. They don't have to be in the same direction, but the vectors must be parallel. Like when we learned about vectors, vectors in the x and y direction don't interact. Vectors that are perpendicular don't interact. So they have to be parallel. Either both up or both down or up and down. Yes?
To follow up on that, the only reason we use 70 is because the M1 is moving on a plane and M2 is dropping.
Right. Exactly. We care about the dropping force. M1 doesn't have any dropping force. These are called Atwood systems. So when we have one net force acting on multiple objects, we call it an Atwood system. We're going to investigate this in a lab next week. Michael.
So the gravity doesn't act on M1. Is that because of normal force?
Yes. Yeah. Normal force keeps it from acting. So all we really know is that, or all we really care about is the force acting on M2. Now, do you think the tension still equals, is the same on both sides of a pulley? Is T1 still equal to T2?
Yeah.
Yep. T1 is still equal to T2. It's always going to be equal to T2. This is one of those things you should really put in your pocket and carry with you into physics AP and more advanced physics courses later on. When you have a pulley, the tension is the same on both sides of the pulley. Okay. That's all I have. Are there any questions? One, and then two.
So, why is it all